Drilling. We are very pleased to welcome all of you to this program. My name is Leah Lovelace, and I will be your moderator for today's seminar. Please note that today's call is being recorded, and all participant lines will be muted during this broadcast. If you are listening to the program over the phone and you need assistance at any time today, please press *0 and an operator will assist you. If you are experiencing technical difficulties with the web portion of today's program, please email spe@compartners.com. Today's presentation will last up to 90 minutes and include a specific question and answer period. However, you can queue up a question for us at any time during today's presentation. You may submit a question by typing it into the box in the lower left corner of the window. Then be sure to click on the send button located next to the box. These instructions will be repeated later in the program. And now it is my pleasure to introduce Jenny Cristanti to introduce today's speakers. Jenny, please go ahead.
Thank you, Leah. It's my pleasure to
Thanks very much, Jenny, and thanks everybody for calling in this morning. Really appreciate it.
Currently Vice President
appreciate
SPE
for giving me the opportunity to
He's a leading expert in the design and delivery of automated managed pressure
go
drilling
right along
system.
here. We've got an hour,
Mr.
hour and a
Reisma
half
holds a master's
to
degree
work
in
with.
petroleum
Hopefully
engineering
keep
from
us
the
on time
University
and
of New
give
South
you guys
Wales,
lots of
Australia.
everyone lots of time
He
for
has
questions.
more than 30 years of
So
worldwide
just the outline for
offshore
today's
industry
presentation
experience in
is,
drilling,
of course, what is
completions,
MPD,
workover,
if
and
you
production,
don't already know.
both in engineering and
And,
operation.
you know, when should we
In the
use
past
it?
10 years, he
What
has
does it
focused
do?
primarily on developing and
How do you
delivering
do it?
automated
there are
bottom
many
hole
ways,
pressure control
of
and
doing that.
automated
Hopefully,
tip detection
give you
systems
some flavor
and
for that.
contributing to industry
What's the benefit, and then just wrap it all up. So those are the general questions
in the SPE
that I'll be trying to answer. And
Mr.
certainly a lot
Reisma
more questions,
holds numerous
to
patents
that,
and
sure.
has written and co-written
So I'm just going to start with the
various
IADC
articles on
definition.
the subject of
And
managed pressure drilling.
this definition was
And,
developed some years ago after several years of actual discussion about it. But what we came up with was to say... Thanks very much, Jenny, and thanks everybody for calling in this morning. We really appreciate it and control the annular pressure profile throughout for giving me the opportunity to present. You know, that could be in the casing, that could be in the open hole section. Go right along here. We've got an hour and a half to work with. Then manage that annular hydraulic pressure profile according to some limits. So those limits the outline for today's presentation pressure. Of course, what is MPD? The fracture pressure. You don't already know. The borehole stability. You know, when should we use it? Borehole stability. What does it do? Something that people don't always think about. How do you do it? But in some applications, that's the primary doing that. Hopefully, consideration. Give you some flavor for that. Also, what's the benefit? You know, what we want to do with MPD is avoid a continuous influx. It's really an overbalanced drilling technique. To that, I'm sure. And the reason we came up with that was because the IVD, or underbalanced drilling, was already out there. This definition was and there were really, to be honest, some people that just didn't want underbalanced drilling on their rigs or in their region. And we wanted to make the distinction that managed pressure drilling wasn't there to have this continuous influx and profile throughout the well, you know, underbalanced drilling. You know, that should be so what we're going to do is if there is an influx, it could be planned if you're trying to fingerprint your well and then manage figure out what these environmental limits are. But you're going to contain it and deal with it. Of course, and core pressure, be drilling over balance, fracture pressure, and the bullet points that go along with that are, you know, it's really just a collection of tools and techniques. But in some applications, a little bit more. And what we want to do is get the well to TD at the lowest risk. You know, what we want to do with MPD is, you know, avoid a continuous influx. It's really an overbalanced drilling technique. That sort of thing. And the reason we came up with that was because UVD, or underbalanced drilling, was already out there. And there were really, to be honest, some people that just didn't want underbalanced drilling on their rigs. We run into region problems such as loss. We wanted to make the distinction that managed pressure drilling wasn't there to have this continuous influx and underbalanced drilling. So what we're going to do is if there is an influx, it could be planned if you're trying to fingerprint your well. You may be able to just change the pressure, figure out what these environmental limits are. But you're going to contain it we want to make sure that we're getting to target. Now it says economically unattainable prospects, but you know really what we're looking at is efficiency here. So we may be able to get to TD with conventional drilling. However, using adding MPD techniques may make it more economic and easier. So when should we use it? And just to follow on from that, it's really when, conventional drilling is not getting us to where we want to be. So are we going AFE, over AFE because of drilling problems, losses, kicks, that sort of thing, a lot of non-productive time. So we just want to come up with a tool that we can exploit the asset at the lowest risk cost. So what are these problems that we're going to run into, this NPT? Well, as I mentioned, kick losses, borehole instability, and that's going to be characterized by having to back ream quite a lot, and essentially fighting your way to bottom, maybe cuttings, loading, and collapsing, that sort of thing. Breathing ballooning, which we see in high, HPHT wells. Nuisance gas, and that's a little bit of a different one, and it might suggest more of an underbalance drilling technique. And stuck pipe, which could be borehole stability or differential sticking, and then low rate of penetration, which can be helped in some cases with managed pressure drilling. So how does it happen? Well, first of all, what we see is drilling through depleted reservoirs, and what that causes is typically borehole instability and a reduced fracture gradient. So you end up with this smaller window, and I'll get into that, this pressure window, and I'll get into that a bit more. Drilling into fractured reservoirs, if you've ever drilled into a carbonate karstified system or a massive vulgular system or fractures, you get total losses and then turns around and kicks you. This is another one that we've always had a problem with HPHT wells, and how to compensate for the temperature changes in the well, particularly when we're tripping, and that those mud properties have an opportunity to change because of the increase and decrease in the temperature in a particular part of the borehole. So how are we going to manage that? And surge swab. A lot of re-entry drilling is done, very high friction factors in the well, and when you start moving that drill pipe, of course, you'll get increased pressure from surge swab. Exploration wells, do you really know what you're drilling into? Basin models greater than 5 pounds per gallon error, for example. We've got one where we just drilled in, it was over 2 pounds per gallon. Total losses, and we had to correct for that. Sorry here. And deep water, narrow pressure margins, if you've seen that. Again, that's something that's just beginning to be seriously looked at in terms of providing solutions, and is going to be very important to ensure we obtain those reserves. So, these problems are costly. Definitely, if you've gone twice over AFE in some cases, just your expendable cost, that's going to be a lower cost type of thing. Your spread cost, of course, that's going to be a higher price. But the greatest cost is that lost objective that the oil company was trying to obtain. So if you lose those resources, you just don't have that money anymore. So what we want to do is we really want a lowest dollar for recoverable barrel of oil equivalent. And we're going to reduce those dollars by controlling the drilling costs and then increase those dollars by being able to produce those reserves. And that's very real. What I'm talking about here is really drilling the undrillable wells that we can't get at with conventional drilling. So what happens, just basically in this diagram, it's very simple, of course, but what I'm showing you here is this red line of pore pressure or borehole stability, and the other red line here of being the yield or the fracture pressure. And this is this typical narrow window that we run into, and what happens is when the drilling rig turns their pumps on, for example, the frictional pressure increases, and we perhaps exceed the yield pressure, and we start getting losses. And people will look at this and say, well, we're getting losses, let's pump LCM, let's pump borehole strengthening materials, and those may help to a degree, they may even solve the problem. But what if they don't? What's the next tool in the toolbox that we're looking at here? Let's try and maybe control this pressure a little bit better. When pumps are off, for example, as well, then we lose that frictional pressure, and because maybe we've dropped the mud weight a little bit to try and cure our losses, as I mentioned, as another method of doing that, we may find ourselves below pore pressure. Maybe not a lot below pore pressure, maybe just a little bit of gas coming in, but enough to make it, somewhat of a kick, perhaps, or nuisance gas, and it's not something that's controllable. So all these things are going to add up. You maybe get to TD, but what's this additional cost that you're going to incur just because of this one situation that you have here? And this could be in a specific portion of the borehole as well. It could be 3 or 4 meters of a depleted zone or an overpressured zone that's giving you a problem. So with managed pressure drilling, what we want to do is we want to really control that, work within the environmental limits. Perhaps we've established what those are by a leak-off test and what we call fingerprinting by maybe reducing the pressure and taking a slight influx to find out where our pore pressure is. And by some way of manipulating the pressure, we are going to maintain the pumps on and pumps off pressure within this window. So, what we get into a lot is the pressure uncertainty, as I mentioned to you in basin modeling. And in this example here, what I'm showing you in that gray area, and literally it's a gray area, is we're trying to figure out where our fracture gradient is, and we're not quite sure where that is. So the red line is the fracture pressure here. And the yellow line, if you can see that, is the pumps on pressure, if you will. And then the green line is the pumps off. So what happens is, yes, we're staying above the blue line, which is pore pressure, so we're not taking a kick. But when those pumps go on, look, we get into this gray area. And that's an uncertainty that we have to manage, because that may be where our fracture pressure is, for example. So this is just adding on from that last basic example that I gave you. So this is a real well where we're, somewhere between, just under 17 pounds per gallon or up to 17.5 pounds per gallon for fracture pressure. So what we're going to do, again, is come up with this managed pressure solution. And what we do here is, if we see the MPD, this purple line, this MPD mud weight, what we've done is we've reduced this mud weight, and then we're going to apply surface pressure, and that'll be the red line. So we will keep the pressure in the well bore above the pore pressure, but still below the fracture pressure. So this is I'll get into these techniques a little bit more, but certainly a workable solution for this type of application. So I'll get into the how do you do it, and really, 4 main parts here, and they're all very, very important in my estimation. And that's really, you need to engineer this solution. You're just not going to go out and start saying, well, I'm going to do MPD and I'm going to change the pressure and whatever. You really need to, engineer it, plan. People have to be trained. They may not have ever seen the equipment before. They may not understand what you're trying to do. So that drilling rig crew has to be trained, particularly the drilling supervisor, because it's a new technique. So with anything else, if you've got a new tool, the person that can use that tool the best is the master craftsman. So really, we want people that know how to use these tools to the greatest effect. And that'll give us the execution that we do, methods, and the results that we desire. So in engineering, let's take a look. Let's just see if managed pressure drilling is a tool that can be used to drill that well better. We're going to have the hydraulics program, so we're going to plan on how, what mud weight we're going to use, what pressures we're going to use, how that's going to affect the pressures all along the annular pressure, the pressure profile, which is very important, and I'll give you some examples of that. And then tripping is probably the most important thing we need to look at. Drilling is essentially easy in terms of maintaining pressure and having pumps on and pumps off. But how do we get that drill string out of the hole? Are we going to pump pills or use a different weight of mud? How fast are we going to pull? Are we going to pump out of the hole, or are we going to go on elevators? Obviously, if we can get out on elevators and along a hole section, it's going to be much faster, much more efficient. But it may be necessary to pump out of the hole. You just have to run these hydraulics to see really what you're going to do. And then running casing and liners, you ended up with higher surge swab pressures, that sort of thing. So how are you going to get the casing in the hole? And finally, how are you going to cement this well? So if, don't start pumping cement and then get total losses, for example. So really planning from drilling out of the shoe to landing and cementing and casing, or your liner, if that's the case. So we really need to look at the whole thing. Okay, just in design, what I'm showing you is a typical hydraulics diagram that we have, and it's showing this is using back pressure, and what we're going to do is we're going to try and control the pressure, and it says in the pink there, connection 170 psi, a connection at 300 psi, connection at 500 psi, and these would be to offset friction or try and maintain the pressure in the window. So we've got measured depth along the left and equivalent mud weight along the bottom here. So the mud weight is changing with depth, and I'll just click ahead here to explain what we're going to do. And the dotted line there on the left is our pore pressure, for example. So what I've shown here is that and how we're doing this is a constant bottom hole pressure. We're going to try and maintain that at the shoe. So that's the constant bottom hole pressure is the intersection of the dynamic pressure when the pumps are on and the static pressure when the pumps are off. So and we're holding back pressure. So I'm really intersecting this line, this pink line and this black line. The black line being the dynamic pressure with the pumps on, and essentially no back pressure. So we're going to hold pressure at the shoe here, and what you see is that window extends all the way down to the base here and up at the top here. So you see how this line curves. So that would be the pressure throughout the well bore as we're drilling, and we're going to maintain 170 psi on a connection. So we have to be aware that the pressure doesn't drop below the pore pressure here, this line here, and then maybe some fracture pressure or borehole stability pressure, which I haven't shown here yet. So I've said this has the maximum fracture pressure tolerance, FP being fracture pressure, and the minimum pore pressure tolerance. Why? Because the pressure profile moves to the left or towards the pore, it reduces, so it goes towards pore pressure. So you have to be really pay attention to that change in pore pressure, and that it's or that pressure in the well bore, that it approaches pore pressure. So if I show the next slide here, what I'm going to do now is I'm going to intersect the green line and the black line, and that's kind of the midpoint, and I may want to have that as this is my narrowest window between pore pressure and fracture pressure, and I want to hold the pressure constant there. What happens is I see my pressure is going to increase at the top here at the shoe, and it's going to decrease a little bit more down to TD here. So, and finally, what I'm going to do is I'm going to say, well, what if I wanted to hold a constant bottom hole pressure at the total depth of the well? And that's where I want to get to, obviously. But look at what happens up at the top here is this pressure really increases up at the shoe. So I have to pay attention to that. I'm not going to be concerned about pore pressure because my pressure is never going to drop there. So here's my maximum pressure condition. So this is just part of the part of the engineering and hydraulics analysis that we're going to go through. And why do we do that? Is because, okay, sorry, there's the pore pressure there. Sorry, the dotted line was actually minimum mud weight. But there's the pore pressure. There's the instability pressure. So I'm saying borehole stability pressure, BSP here. And what's happened is that pink line has now moved into this borehole stability area there. So what that's saying is I drill deeper, I'm going to run into maybe some borehole stability problems with managed pressure drilling. So I don't really want to do that. If I then say, well, here are my fracture pressure out here, so FP for fracture pressure, if my pressure exceeds that line, then I'm going to get losses, and that's the solution that I end up getting if I'm keeping a constant bottom hole pressure at the total depth of the well. So you see the pressure doesn't stay constant as we're drilling. We're really just holding constant pressure at a point, and the pressure varies by depth. So we wouldn't really want to do that because we're going to get losses. But the solution is going to be that we hold this midpoint pressure. Why? Because the pressure down here is still higher than our borehole stability, and our pressure up here is less than our fracture pressure. So really what we're drilling is in this window, which is what I showed you in that very simple cartoon a few slides back. So it's not that simple to come up with these solutions sometimes if you've got a lot of variables in pressure in the open hole section, for example. So that's where, you know, we have to do the work there, but we also have to do a lot of work with the planning, with the site survey. It depends on the equipment, the location, you know, the stack height, because you need a rotating control head if you're using back pressure, for example. So these things all need to be considered, and it just depends on the type of installation. But really, you want to do a site survey first, where you're going to put things, how you're going to hook them up. The hazard HAZOP, it's a new technique. There are new hazards. There are new methods that have to be done. It should be included into the drill the well on paper program, that sort of thing. You know, how are you going to manage well control now? How are you going to do kick detection? So those are all very important considerations as well, and how long they take is really, according to your HSE program, the complexity of the well, the experience of the personnel, that sort of thing. Some of the more detailed, you can do several hazard HAZOP reviews as well. So you'll figure out the best way to deliver the product. And of course, mobilization. How long does it take for equipment to get to New Zealand, for example? Training, again, very important. Office people, yeah, basics of MPD at a minimum. If the engineers are designing it, they have to know what they're talking about. Rig operations really have to know what's going on. What if that rotating head begins to leak? What am I going to do? What kind of pressures are we looking at? How am I going to communicate with the MPD provider? That sort of thing. And those not directly involved but like to listen to the morning calls, a general understanding is probably fine. They know what you're talking about. So how do we do all this? I've given you a couple of clues, maybe with back pressure control, that sort of thing. But it's really going to come down to where are you going to do it. There's four main ways. There's annular friction, surface pressure, density control, and what we call delta energy, and I'll talk about that. Now over on the left here, where I say annular friction, that's really the equivalent circulating density control only. You only have control over the friction in the well by using this technique. And how are you going to do that? That's with continuous circulation tools that are available today. So allow you to continue to pump down the drill string while making a connection, and can be very helpful for that. The E&I system, for example, that was just presented at the last MPD UBO conference in Milan. Very good. Same with the CCS system that was used in Norway and other places. Is a different method, but they will only give you control over the friction pressure in the well. Geometry, you're going to design, obviously, to reduce your friction as much as you can. You're going to, that's with the casing drill string, hole openers, a lot of that being done. Pump rate, you're going to consider it, but I wouldn't recommend starting to change pump rate because cuttings are loading. You want to reduce ECD. You're going to just drill yourself into a problem. Rotary speed is another consideration. In some cases, the equivalent circulating density can go up maybe 1/10 of a pound per gallon, that sort of thing. But typically, something you're just going to consider in your engineering, you're not actually going to plan to use it for the purposes of controlling friction. But I thought I'd just throw that in there. Okay, so our surface pressure, which is going to be the most common we're using today, is manual automation or automation of chokes. Density, this is typically where we're looking at highly depleted reservoirs. So we're going to go with a single phase or a two-phase flow to manage those pressures. And then delta energy are these mechanical lifting devices. So we're looking at, in some cases, deep water, in some cases shallower water, but essentially trying to reduce the mud weight, equivalent mud weight in the riser to that of a seawater gradient and adjust for the pressure profiles in the well. So subsurface pumps are coming in, and that was presented at the dual gradient seminar that we had in Milan as well a few weeks ago, which was very well attended and a lot of good information there. So if you can get more information on that, that'd be very helpful. I can point you in that direction too. So I'm just going to talk about surface pressure. Really, we don't have the time to go into every method that we can think of for managed pressure drilling, and I think that the number of methods being developed and are increasing by the day almost, and it's really just coming up with more creative ways to get our wells drilled cheaper. But what we've got, we're getting developed, is this IADC selection guide. And this is only in draft form, and we're still working on it a little bit. But what we're going to be interested in here is, what well location. We're really just trying to provide a guide, a simple guide to start you off with, and some of the tools that you may consider for managed pressure drilling. And I think today what we've got is too many tools being selected by this guide. But in any case, we're still working on it a little bit. Hopefully, in a few minutes, you can get an idea of whether it's going to work for you and what could work for you. So we're going to look at what your well location looks like, the type of rig, the drilling fluids in use, what is the pressure profile. Really, what are your goals or concerns, or are losses, kicks, that sort of thing. And we've got just an example of the narrow pore pressure here, frac gradient margin. And then what it comes up with is, and I won't go through all the colors and everything, is the different techniques that are available. And if you just go, briefly look down this list, you can see quite a number of different techniques that can be used. And they come under the managed pressure drilling umbrella. And we did sneak in underbalanced drilling systems here. Why, I don't know, but it's a consideration as well. So, and there are a number of comments and things like that. So I think it's going to be a very useful tool just initially to someone to take a quick look, and there will be reference materials linked to this as well, papers that you can read, that sort of thing, to give you more information about that method. it should be out in the next couple of months as well, if we get back to it. But this is all done in committee, and things don't move fast in committees. So, just to go back again to presenting another way to look at this narrow window with conventional drilling, a little more to from the cartoon that I showed you earlier, is here we are trying to drill with conventional means, and the red star just says, okay, my constant bottom hole pressure point is at surface. That's how conventional drilling works. We're at atmospheric pressure. But what happens is our static density is down here and creating that pressure, and our circulating density is over to the right, creating that pressure. So we don't, they just keep getting broader and broader. Why? Because the hole gets deeper and deeper and there's more friction. If I had my problem here, which is I've just arbitrarily put in the pressure boundary that I need to get through, this narrow pore pressure frac gradient boundary, for example, or borehole stability boundary, which may be because I need to drill through a depleted reservoir and I need to get to a deeper horizon. I can't do it because I'm outside that boundary now. So I need a different way of getting through, and this is becoming more and more common. This is a real brownfield type application where we're in an existing field and we're drilling deeper to a new target. Continuous circulation, just one slide briefly on this, and how I'm saying we've got ECD control is on the left here. What we've done is we've maybe reduced the mud weight a little bit, and we would be taking a kick, or we're keeping the same mud weight. But this line here, our dynamic pressure with pumps on, is always going to be designed to be able to drill through that window. So that's no problem. We've got that. Now, on the right here, what we have to consider is that once we're at TD, and let's say the bit is right there, we've got circulation occurring, above the bit, obviously. But below the bit, what we've got is the static gradient of that mud. So we're parallel to this dotted line. So we have to make sure that when we're pulling out of the hole, that we still maintain this pressure in this window here. And we couldn't pull all the way out of the hole without doing anything. Obviously, we'd lose all our friction, and we'd be back to this point and taking a kick. So what we're going to do, plan on is maybe pumping uphill to impart more pressure to increase this as we're increase the static density without circulation. So that's the engineering plan, but this is just to show you, what you'd have to consider with continuous circulation, because you only have circulation to work with and the control of the friction. So going on to back pressure control is, it's really the most common method used today, onshore, offshore. It's scalable. People are using it in manual control. It's as a backup in case they need it. It's planned, so we are going to use it, that sort of thing. So there's a real whole plethora of ways to apply back pressure in order to do that, and I'll talk about that a little bit. But what does back pressure control do? Again, just trying to build on from those cartoons that I showed you earlier. If we wanted to maintain constant bottom hole pressure at the total depth of the well, and we planned for a static density with back pressure of some value, which is going to be above the continuous the pressure when we're pumping, continuous flow, we can find that we can get, if I've done this right, we can get through that pressure window in that way. So that's another way of getting us to TD and staying in the pressure boundary. And rather than calling this constant bottom hole pressure, what I think we should really call it is inverted pressure drilling, because instead of having constant bottom hole pressure at the surface with conventional drilling, I've now just turned it upside down, and I've got constant bottom hole pressure at TD. And why does that work? Mainly because I have less friction in the open hole section, and I'm compensating for all that friction from the shoe right to surface. So a little bit of a math exercise there, but works very well. Okay, let's just say I'm going to drill a well, and all I know is somebody's giving me a fracture pressure at some depth if I'm lucky, and maybe a pore pressure. And this is the start of figuring out how I'm going to drill this well. So that's all I've got to start with here. FP is fracture pressure and PP is pore pressure. So I've managed to get my shoe down, and maybe my fracture pressure is my weakest point is at the shoe. I hope not, but it ends up that maybe it is. Maybe I've landed the shoe too high, and it's not like that hasn't happened before. So, gosh, now I've landed the shoe too high. I've got a weak shoe. What am I going to do here? So I'm going to hold constant bottom hole pressure at the shoe, and I'm going to drill down. And that little red star here is saying where I'm going to hold this pressure constant. So here's my static density and my equivalent circulating density. And I turn the pumps on, and when I turn the pumps off, I'm holding pressure constant here. And what I'm going to do here is just a little exercise of wherever my bit is at, that's where I want to hold the pressure constant. And let's see if that actually works. So if you can just imagine that red star being the bit. So I'm going to drill ahead, and I'm still okay. You know, I haven't actually drilled. This is my hole here, and I'm not down to pore pressure yet. So I'm okay so far. I'm staying away from fracture pressure. I've got a pretty big window there. So I'm okay. I'm going to just keep drilling down, and now I'm at the midpoint of the open hole, and things are going really good, and I'm getting closer to my fracture pressure now with my back pressure. So I'm just going to keep drilling ahead. And I've now gotten to TD, and it looks like I could be hitting my fracture pressure with my back pressure. And if you remember from the hydraulic model that I showed you, you know, with constant bottom hole pressure at TD, where you've got this curve, I'm not showing you the curved line, but that the pressure is going to increase at surface. Why? Because we're compensating for the friction in the open hole in order to keep these values constant. So this pressure is going to go up as I'm doing that. Okay, so maybe, you know, the best thing to do would have been to stay at the midpoint of open hole or at the shoe. But let's just keep going ahead here. I'm going to show you what happens if you pull out of the hole, and now you want to maintain that pressure constant. So you can see where I'm at the fracture pressure there. So what I'm going to do is I'm going to start looking back a little bit. And, okay, well, if I held my pressure constant here, okay, I don't have the pressure as high there. I'm okay. I'm not at pore pressure. And this is what's going to happen if I'm a little higher. Here I am back at the midpoint of the open hole. And really, this looks like the best solution, again, like I showed you with the hydraulic model. It honors being able to stay away from the fracture pressure and stay away from the pore pressure. So really what I'm suggesting to you is once you selected a depth where you want to keep the pressure constant, don't mess with it too much. Because if I keep pulling out of the hole, and this is similar in some respects to the continuous circulation where I'm not controlling you know, so much the pressure profile here as I am here because I don't have circulation below, here, and I don't have circulation below the bit. So my pressure is going to be dropping a little bit in that line. And I'm now getting back to the shoe, and what I found out is when I got back to the shoe, now my equivalent static density with back pressure has approached pore pressure here. So that's just how the pressures can change in the borehole and how I have to consider those when I'm drilling this well. So what I end up with is a potential pressure window that I can drill in with surface pressure. So, and these dotted lines here are going to be my back pressure, right, when the pumps are off. And this line here, this white line, is what the pressure profile looks like when the pumps are on, is that pressure line when the pumps are on. So I can manipulate the pressure anywhere in this window by changing the back pressure. And I just have to figure out where I want to do that. So do I want to move the line here, or here? You know, so this line is somewhere in between this line and this line, and to stay between in that window. So this is the potential pressure window that I have, and I'm just going to figure out the best place to be in it. And really, I want to stay away from fracture pressure and pore pressure or borehole stability problems, and manipulate that pressure. So how am I going to do that? You know, this is a surface pressure installation, surface back pressure installation here, and we have a rotating control head. We have a choke manifold. We maybe have a controller here, but it could be a manual system as well. And so that's an interactive controller interface, that sort of thing. So all I'm going to do is I'm going to, on the return flow line here, I'm going to maybe impart some back pressure with this choke manifold. And then it's, if I've got a little bit of gas coming through, it may go to the mud gas separator. It may just go to the shakers. It may be connected as well somehow to the well control system, but those surface piping arrangements can be changed anyway. We might have a pressure while drilling sub downhole that tells us really what's our pressure when we're drilling, so we can make modifications to the back pressure if our models aren't correct. And importantly, we've got a non-return valve, because when we turn our pumps off, we don't want flow going back up the drill string. So essentially, that's what we're looking at there. And this is an example of a simple installation where we just have a choke manifold, and this is actually, you can see some control lines here and hydraulic line, and we've got this connected to a control system. But it's we're using 3-inch hydraulically actuated chokes, which is kind of the stalwart of back pressure control. If you want to look at a clearer engineered solution, this is one that we look at. And again, we've got how is stack height going to affect us? What are we going to use for a rotating head? A detailed piping diagram, a sized mud gas separator, maybe a flare, and that could be because we do get some gas and we're just going to flare it off, and then continue drilling ahead. And this is where these nuisance gas applications come in, and essentially they're a low volume, high pressure situation where you'll temporarily actually go to an underbalanced situation, but you will essentially bleed that gas off in a well control event type of manner, and then continue to drill ahead without having to wait up, because you'll deplete the reservoir. So this is another type of manifold setup using, these are the auto chokes here, and then a third choke's been put on the E-choke. So this would be, these chokes here, the auto chokes, might be a lower pressure control, and the E-choke might be a higher pressure control. So there are, numerous ways of designing these systems. A full-scale installation, a lot more parts and pieces added on here, but essentially, if a back pressure pump is being used, it may aid in more precisely controlling the pressure, but it adds to the piping, and you need strainers, that sort of thing. As well, if you're not using a kick detection system already, add in a Coriolis flow meter, which then gives you a really high fidelity kick detection method, probably down around 15 gallons a minute in order to detect. Depends on the flow rate. It's a percentage of the flow. that the users are going to be able to pick up. So it's more piping and more equipment, so obviously more complexity involved. In a lot of applications, this is the standard method of doing managed pressure drilling, but you know, I wouldn't say for some of the North America land applications where it's more of a contingency or a known requirement, and you can trap pressure, for example, that you just wouldn't go ahead and use that. So here's an installation offshore, I believe, in Malaysia, and you can see the automated choke manifold sitting on the deck here, the pump, and actually the Coriolis flow meter is sitting right up here with that bypass line. So because there's no deck space available, that's where it was put. Here's the generator, and that's needed for this back pressure pump because it's something like 110 kilowatts of power to start it. This is another offshore situation. You see the Coriolis flow meter here, and in this application as well, there are two back pressure pumps, and the client just felt that, you know, they wanted the contingency of a backup pump, and that's fine. You know, this is what you're going to do when you go through your HAZOP, for example, and you're going to see that. Here's a land application over here where we've got twin hydraulic power units. This is a modular system. That's the PLC panel. That's the pump. That's the choke manifold. On the integrated system, it's got the PLC, the hydraulic power unit, and the choke manifold all on the one skid. So different applications, you know, depending on and different methods depending on that application. I'm just going to roll into a little more detail on choke control automation and then wrap things up. But here's an early automation attempt at controlling a choke, and I think this goes back to 1967. But really, you know, he wanted an entirely automatic operation of that choke, and here's how you're going to do it. Don't ask me to explain it. I don't know. I'd have to go through it. But it looks a bit complicated to me, and although that was the state of the art at the time, it just didn't work, and was likely unstable, unreliable, couldn't be operated. People said, I can do it by hand better, and that's what they did. But the reason they wanted that automation was because they want it repeatable. What we have today is what are called PI control blocks, or proportional interval blocks, typical control system method. Some manual tuning is required to get the right numbers into this PI control block. What happens then, though, is if the compressibility of the well changes, you need to go back to square one and do your manual tuning again. These aren't the most stable systems in the world, so rapid large changes in pump rate or pressure requirements can make the system unstable. So typically we're very controlled in how things are done on the rig. At times, though, you know, things happen without planning. Pumps stop their power failures, that sort of thing. So the system has to compensate for that, and sometimes what they do is they go back to manual control, and we're trying to get away from that. The chokes have this sweet spot of 20 to 80% or 30 to 70% where they operate very well. If you move the choke, you get a pressure response. But below those numbers or above those numbers that I'm showing you, if you move the choke, you may not get a lot of pressure response, so you have to move it a lot, and that makes it really difficult to control. And as luck would have it, a lot of jobs we're on were below the 30% range, so it's difficult to control these chokes manually. It makes it a little easier with PI control blocks, but really what we want is something else. And what you can refer to as well as Alexi's paper presentation that he gave. It's not a paper, sorry, it's just a presentation from the 2011 NPD UBO conference on that. He does a very good job of explaining it and demonstrating it. So with a new choke controller, we want it to be compatible, have no tuning requirements, so people don't have to know how to work it. They just have to know to be able to put a pressure signal to it, either manually or whatever, and the choke will do what it wants. So it has to operate across the full range of the choke. Why? Because we want it stable, and stable because we don't know what's going to happen, whether it's low flow or people changing pump rates or different fluids going through the choke or compressibility changes. So this is where we're looking at now. So it would be just install it, go through the calibration routine, give it the pressure you need, and drill ahead. And really, that's what people that are really good with manual control of chokes do. So we did a field trial, and this just shows some erratic flow rates and pumps off and on rapidly. And this green line here and here, I've just kind of duplicated the plots a little bit, is the flow rate. And the blue up here is the choke position. So, and the choke position is changing according to a set point pressure and the actual pressure that we're seeing. So the red here is the ADP, we call annular discharge pressure set point, and here's the PV, which is the present value of the discharge pressure. So the choke has to match the red line to the discharge pressure. So what happens here, if we're trying to replace friction, is we've turned these rig pumps off, and the choke controller is, this automatic hydraulics program has said increase the back pressure to here, and then we see the choke actually increasing the pressure. And what's happened is, if we look up here, that choke is actually closed completely. And the reason this pressure is kind of sloped is because the well is compressible. So what that tells me is the driller really turned off the pump too fast. And we couldn't build up the pressure quick enough to replace that annular friction. We get a little bit of an overshoot here, but this is the pressure overshoot. And this just goes on and on and on, depending on, where and what's happening in the well. Some very rapid changes, some very slow changes, for example. And that's really what you want to do. You just want this choke just to keep doing whatever you've told it to do, based on what's going on with the pumps and maybe the pipe movement, that sort of thing. Anything that's really going to change the equivalent circulating density or the static density. And so here's just a close-up of that first pumps off situation that I showed you. That was the choke overshooting in order to control this pressure down here. But you see this pressure being controlled here is, like something like 5 psi, and the choke is here. If you see the choke position, that's just barely open, and the choke is actually stabilizing here. So the well is flowing. This is actually underbalanced drilling because the well is flowing for some reason, or it's maybe not underbalanced. It may be because you're injecting nitrogen, something like that. But we're getting some flow through the choke, and it's keeping the choke open 3 or 4%. And that's a good thing, because remember I told you the bad area is less than 20 or less than 30. And what we see is the choke is actually being able to control there. Here's where we're flowing at a constant flow rate, and we're just making minor changes. And this choke is actually opening here for some reason. You see it's increasing. And that's, I think, because this one we're looking at nitrogen coming around, so there's a little more flow coming out of the well. But the choke opens to maintain this constant pressure down here. So that's just doing that automatically. And if you can imagine somebody manually having to do this 24/7, it can get a bit bothersome, and they're likely going to miss a few events. So it'd just be nice to have a choke do this all the time. So what's the overall benefit? Not of the choke, but the overall benefit of managed pressure drilling. And really, here's some of the benefit here. Here's flow after flow. So here we've got the pumps coming off, and in the red here we've got this afterflow. So this is breathing and ballooning, as it says up here, from wellbore breathing and ballooning. And then we turn our pumps back on, we don't get the same return flow, so we're losing fluid. And that's typical of high pressure, high temperature wells. Here what we've got is the green line and the red line agreeing very closely. This is just a back pressure pump. And here what we have is a green line and the red line agreeing very closely. Again, maybe a little bit of losses, but certainly improved by the fifth connection. So you know what we had to do was determine what were the best back pressure numbers to use to reduce the breathing and ballooning. Here's where we've got non-productive time because of saltwater influxes. So a high pressure saltwater zone flips the oil-based mud. So we're really designed the system to be able to not allow this influx of salt water, so maintaining a higher back pressure at that point. And you can see the hours involved here can be very costly. So what we did is we eliminated that. In the Gulf of Mexico, this is Shell's experience with some 24 wells, and really being unable to drill these targets because of these narrow pore pressure fracture and borehole stability windows, and having to drill through previously depleted sections into new reservoir, and it just wasn't possible to do this conventionally. So these would have been, you know, a pretty good chance of being stranded reserves had we not had this technology. So you can, you know, just imagine for a moment, you know, leaving behind millions of barrels of oil and the cost to the company for that. Just a global application, it's really everywhere. These dots don't represent all the places where we've done MPD. And North America, you see the big dot here. That's a lot of manual MPD control, just using a rotating control head as well, which is more of an environmental application. They're just a safety as a diverter, but it's still to somewhat manage the annular pressure profile. Up in Alaska as well, that's a new area. A lot in the North Sea. West Africa is developing. Big time in South America and Brazil. And in Asia, we're very active in Asia as well with the different methods. So it's growing all the time as far as where these applications are going and what we're doing with them. Of course, deep water, Gulf of Mexico, that'll be starting, I'm sure, in the next couple of years with these subsea mud lift systems. So in summary, you know, just use it where you're not getting a good conventional drilling solution. That's my method here. Is, you know, there are other tools out there rather than just pumps on, pumps off, messing with mud weight. You know, you can work out the economics and the method and go for it. It's really, stop beating your head against the wall here. These are proven technologies now. It can be a drop-off or lots of equipment with lots of redundant equipment. It can be whatever you need it to be. There are hundreds of wells have been drilled this way again. You know, with advanced choke automation, I think we're just going to make it easier. So wouldn't worry about that. So really, what does it do? It's really, Ken Smith coined this a few years back, makes problems disappear if you do it right, and you just want to use it and get the oil out at the lowest possible cost. So with that, I've used up my time, and I'm going to thank you for your time and listening, and I'll take any questions that you have.
That's right, folks. We have now reached the question and answer segment of this seminar. Your participation is key to the success of this seminar, so please don't be afraid to ask questions. To enter a question to the web conference system, simply type your question into the box in the lower left corner of the window and click on Send. It's that easy, and we can go ahead and take a few questions from the chat box now. and we can go ahead and take a few questions from the chat box.
Don, first question is it possible to display the MPD back pressure in real time while drilling in Interact or equivalent display packages from other vendors? And if so, how do we arrange this in advance, especially if using a vendor software other than Interact?
Okay, probably the best way is what we do is we use WITS, which is Well Information Transfer System, WITS level 0, and we receive the rig values when we're operating the system. And what we'll do is we will WITS out. We'll send out the back pressure value, choke position, whatever the operator wants to see or whatever people need to see. We'll WITS that back out to the data provider on the rig, and then the data provider can distribute that data to whoever needs it. So that can go to a third-party system. Certainly. Or, what we can do is, if we don't have Interact, is we can connect to somebody's WITS-ML database, for example, and we can use Perform Toolkit or some of these other tools that we have to display the data or move it to Interact. There are a number of different ways we can do it, and we just have to look at each case individually and work that solution.
Another question is how much rig space is required for basic versus a full system?
Yeah, it's really quite a small footprint. If I went back to, if I can just work my thumbnails here, I'll just maybe go back to that basic system. Okay, something like this here is, fits on a flatbed truck, so it would be, a few meters by a few meters. What we've done is we've come up with what we call with the L shape as well, where we've taken this leg and we've turned it 90 degrees, so we actually reduced the footprint even more. So that's just going to sit down by the substructure here. You see, the V-door here, for example. And if I just go to this slide here, this panel, small panel for the basic, is going to sit on the rig floor. For the larger system, we're going to see, this type of a layout here for the equipment. Now, personnel can be either, maybe if this was a mudlogger shack or something like that, we might be in there. We might have our own 10-foot container, or we might be in with the driller, which we're doing on a job right now. So, does that answer that question?
Another question is, could you clarify on slide 11, it's an MPD solution. Is this, the question is if the example is against the IIDC definition of avoiding influx when intentionally using MW below the pore pressure.
Okay, great question. Here, okay, I think that's what we're looking at here, where the static mud weight is below the pore pressure. Now, when we're doing managed pressure drilling with back pressure, what we're going to do is we're not going to allow the well to just go to a static condition. So what we're going to do is we're going to apply back pressure when necessary, and the dynamic pressure when the pumps are on, that friction can increase and remain above the pore pressure. So we're not going to invite an influx. Essentially what we're doing is adding back pressure instead of mud weight to stay above the pore pressure. So we're not going to invite an influx.
Thank you for the clarification. Another question is, with the new choke control, 100% sweet spot, is it possible to drill with zero choke pressure so that with pumps off, the pressure drops to static mud weight?
Certainly, if it was to fail, that could happen. Somebody kicks your cable or does something, or your hydraulics were to fail. I think the reliability's likely up over 99.9%. We haven't had a failure that way. But it's certainly possible, and this is where in your HAZOP, you're going to say, look, when that thing does fail, and even though the risk is very, very low, the consequence could be very, very high, and we need to follow some contingency method of now containing the well. And so you identify that in your hazard ID program, and you develop the solution in your hazard op program. And so that would be, look, didn't give me the pressure I needed, I'm taking an influx, what am I going to do? I'm going to close my BOP, and I'm going to get that well under control. The nice thing is you've got that rotating control head up there, and you're not blowing oil all over the rig floor. So you're bottled up, you're prepared for it. I'll liken this to when we're drilling conventionally, and I think I've got enough mud weight, but I don't. And I drill into I swab in a well, a formation that I hadn't expected. Now what's going to happen? I may have oil all over the rig floor, but my contingency is shut in the well. So I'm going to follow those same procedures. But I've got a different setup now, and which is going to make it much safer. And we're planned, and we're watching what's going on. We expect these sorts of things, and of course in conventional drilling you do as well. That's why you're doing mud pit level monitoring and things like that for kick detection. So that's how we're going to manage that.
There's a question about what is the percent of wells now use MPD? How many companies can provide MPD, and what is the cost of MPD versus conventional drilling?
Well, there are probably 4 or 5 major companies providing MPD today. But you can rent a choke and go and do MPD if you want, and a rotating control head, and off you go. If you got a good engineer and do the planning and things like that, of course you're probably going to be doing it manually. So the major companies have developed their systems specifically for doing this. So what's the cost of MPD versus conventional drilling? Is if you're applying it in the right place, it's a lot less. If you want to look at the overall cost of delivering that well, and the cost if you're looking at risk dollars per recoverable barrel of oil equivalent. Really look at the whole equation here, because if you need MPD and you're not using it, what's happening? You're running into borehole stability problems. You're running into kicks and losses. You're having trouble getting casing in the ground. All these things that aren't in the AFE and aren't part of the plan, unless you're really being honest with yourself and really planning for that. So the cost has to be less overall for delivering a solution. Right? Now the day rate is going to be higher. The number of days are going to be less, and you're going to have a greater assurance of getting to total depth.
Thank you. There's a question about cementing. It was mentioned briefly at the introduction, but the question is, what are cementing considerations under MPD conditions?
Yeah, the same pretty much as drilling. You're what fluids are you going to be circulating What's your annular friction pressure profile going to look like as you're pumping, a lead slurry, that sort of thing, tail, that sort of business. So essentially what may be happening is increasing that hydrostatic pressure first off, and then when that cement is setting up, as it loses hydrostatic pressure, you're going to have to compensate for that. Otherwise, you may may have a gas influx occur and gas contaminate that cement. So it's really just looking at it a little bit closer as to what pressures you're going to generate and how are you going to compensate for them.
Thank you. The next question is, if the rig lost power for a period of time while using the system or holding back pressure on the well, what will happen? Would you get a kick?
Well, that's part of the has-op contingency plan as well. Typically, the systems are designed so that if there is a power failure, which and we're running hydraulic chokes, we've got UPS systems on the control system, battery backup, that sort of thing. So if we lose power, the rig pumps go off. We're able to control the pressure for several hours, typically. And then if that's going to be a problem, then we go ahead and we do a hard shut-in on the well. So we're just going to button the well up and maintain that surface pressure. Now, if it begins to leak off, and I haven't seen this before, what we're going to do is the worst we're going to get down to is equilibrium, and it may leak off into some formation. And where I would get concerned about that is in a borehole stability problem. I don't want to drop below borehole stability and then have the hole start to fall apart on me. So that's a big consideration. Pore pressure, not so much.
The next question is regarding safety. It's generally believed that MPD is a safer drilling method when drilling narrow windows compared to conventional overbalanced drilling. But there was a blowout in Canada where an MPD operation drilled into a fault and took a large kick, burning the rig down. So the question is, do you actually have statistics on the performance of MPD compared to conventional in the tight margin wells?
No, I don't have the statistics other than our own, which is, we've never had an incident as far as some of the other majors have not had, catastrophic incidents either. I can't really comment on what's happened up in Canada. I certainly know about the Neighbors 9 incident, but there's no report out on it yet. So there's nothing that I can comment on. But generally speaking, this is the planning. This is the has-op, the drill well on paper exercise. What are your surface pressure limits? What can you do with managed pressure drilling, and what should you be doing with conventional well control? Because managed pressure drilling isn't considered to be a well control technique. I guess by definition, we are controlling the well pressure, but when there are a significant influx or kick, that's not typically something we'll do with managed pressure drilling. We won't manage that kick with managed pressure drilling. It may be a very small influx, and there may be limits to that. And if you look at the NTL, notice the leasers for the Gulf of Mexico, there's a matrix on how you will control an influx, for example. So, whether it was MPD, UBD, or conventional drilling, there was a blowout, and somebody exceeded the range of the limits of the system to cause for that blowout to occur. There was some human error, or whatever these reasons are for blowouts to occur. So, I don't think you can say something is 100% safe, but safer, yes. I think with rotating control heads, very accurate hydraulics modeling, attention to what's going on with the pressures and the flow makes an operation safer.
Thank you. Can you comment if coring under MPD fileable, and what are the limitations and the requirements?
I don't see why coring. In fact, there was a coring presentation for underbalance drilling given at the last conference by Kuwaiti Oil Co. I think, anyway, in Kuwait. It was really interesting, and I've done underbalance coring myself. Managed pressure drilling, there's really no reason why you can't. Wouldn't be any different. I think the only consideration is now you're retrieving a core barrel. So if for some reason you were to, pull out of the hole under pressure, then you need to be able to lubricate that core barrel out of the well. So you need sufficient lubricator at surface to be able to retrieve that core barrel. Typically, that's not what we do. Typically, what happens when we're drilling managed pressure drilling and it comes to tripping out of the hole is we will circulate the well to a heavier mud in a controlled manner so that we can trip out without pressure, or we're maintaining some pressure just for hole fill and swab compensation purposes. Then when you get your BHA to the surface, you can, you're just pulling out, removing your rotating BOP seal, and the well's dead, and you're just handling the BHA as you normally would when you're drilling conventionally.
Thank you. The next question is, what is being done by the industry to integrate higher resolution seismic information while drilling to anticipate abnormal pressures ahead of the bit?
Well, you're out of my league, but I was at a workshop a few weeks ago, an ATW hosted by SPE in Thailand, in Phuket. I know it's hard business, but I got to do it. And that's exactly what we were discussing, is how do we get greater certainty in the frac pressure, pore pressure profiles. And there's a lot of work being done with seismic look ahead and seismic, rapid seismic reprocessing based on log data being fed. So, you can get maybe a 24-hour look ahead, that sort of thing. I don't think, there wasn't a lot of discussion, and not saying that's not happening, but there was no discussion on actual, real-time seismic and for look ahead. But they're certainly, correcting the models and getting much better resolution and accuracy is achievable. Correcting the models. But you got MPD, and it helps you with the uncertainties anyway. Like I mentioned, we're a couple pounds per gallon overbalanced. The frac pressure was just predicted way too high, and we got losses, and we were able to manage that using managed pressure drilling in a very controlled and safe way of doing it, which kind of make you nervous, cutting back mud weight just conventionally. But you can do it, quite safely with managed pressure drilling.
Someone here asked the question, why continuous circulation is really not a constant part of MPD?
Yeah, I guess, I can't really say. I guess maybe it's just not needed. You find a different way of doing it. That sort of thing in it, or you just don't have the applications like with the NOV system, and that was developed under JV years ago, and I think was really applicable for some applications. It's a big piece of kit. It's an iron roughneck with BOP and with rams and things like that. So it takes time and rig space and things like that. So you look at it and you have to evaluate whether, you know, you can actually get it on your rig to begin with, and if you can, what's it going to do for you, versus other methods. You know, some of these the other techniques like E&I with the valves on every stand that, you know, has got the side port on it. You know, are you going to run one of those every stand and use that? But it can help you if you're using it in combination with back pressure control. But if you don't need it, if you could just do it with back pressure control, then, you know, if you don't need it for hole cleaning or you know, other purposes, then you wouldn't do it. So it's just really evaluating each technique for a particular application.
Okay. Can you comment if is MPD significantly applicable to geothermal well applications as well?
Not really. It can be. Depends on the geothermal application. Shallow geothermal, I would say no. A lot of air drilling goes on. You know, it's not conventional drilling. Is it managed pressure drilling? Yeah, you're managing the annular pressure profile, you know, through air drilling or mist or foam or something like that. So you know, it fits in the definition. For geodynamics in the middle of Australia, if you'd ever like to visit there, I welcome you to do it. But, you know, that's a deep geothermal application with fractures and high pressures and temperatures. And that's a definite managed pressure drilling application. So again, you know, it's what geothermal application are we talking about, and how can we best get that well to TD?
Okay. Next question is, could you identify the impact on well barriers with various surface back pressure systems?
The impact on back pressure. Okay, I'm not sure I quite understand that question. I'll just take a shot at it, and if somebody wants to comment a little bit more on that, clarify it for me. But okay, what we've got is the API. I'll start off with, you know, we've got rotating control heads out there that are essentially diverters, have not maybe been pressure rated or arbitrarily pressure rated or based on the rotation speed, or whether they're in a static position, or whether you're stripping the pipe in and out, having a different controlled pressure limit. So anyway, those things all affect the pressure rating of that barrier. And you know, as a something to make sure the fluid doesn't come out on the rig floor, it goes through the choke manifold. And you know, what we did was a few years ago, John Romello put a huge amount of effort into this. It was a writing of the API 16 RCD and testing it, manufacturing and qualification of these rotating control devices, these barriers for managed pressure drilling. And we're in the process of going through that again and really understanding what it is, and then how do we really want to see them qualified. And this is where it's important in the engineering to look at that barrier and say, is it going to be able to withstand the fluids that I'm putting in the hole, because it's got rubber and I don't want this thing to melt on me, you know, because of temperature or you know, interaction with a drilling fluid. Does it have the rated pressure necessary when I'm reciprocating or rotating that drill string, and when that drill string is static? So those are really important things to look at, and from the supplier side is to ensure that it's a quality product, like the you know, everything's been manufactured properly, and this is what the API 16 RCD seeks to ensure that we're providing a quality product.
One participant is asking if you could describe how the Coriolis flow meter detects a kick.
Oh, that's really easy. It's a pressure sensor. Big secret. But it uses the Coriolis effect, which is measuring the change in, without getting into too much detail, I'd say go to Emerson's website, and there's I think a cartoon video there showing how it works. But essentially, it's picking up the movement of the tubes. They're excited, and then as additional flow goes through, what you see is the tube twisting, and it picks up on that, and it's got a fairly complex algorithm, I would guess. I don't know what it is, to differentiate that movement of the tubes and saying, is it a density change, is it a flow change? So it really detects mass and mass flow. It's really a mass flow, converts it to volume and to density.
The last question here is, can you comment on what application experience that you have within Africa?
Within Africa, West Africa, offshore, Cameroon, been up the river, up the creek, so to speak, with that. So yeah, that's really speaking to a lot of around mobilization. The applications in Africa that we've been on for managed pressure drilling are really not that different than anything else we see in the rest of the world. Yeah, drilling through depleted reservoirs, exploration areas, that sort of thing. But it's really important, that everybody, because we're maybe a long way away, we don't have, fully established bases there or something. It's really important that we sit down, we go through, do the training of the crews, that sort of thing, because they have, in those areas, they have not had a lot of exposure to managed pressure drilling. We sit down, we go through, do the training of the crews.
Wonderful, thanks. And it looks like that's all the time we have for Q&A today. I'd like to ask our speaker if you have any closing comments.
Well, I just really appreciate everyone's time, and you've got my email address there if you want to contact me directly, but I'll also encourage you to use the SPE UBD MPD Technical Interest Group as well to post any questions there. I'd be happy to answer them. There are a lot of experts. I think there's some 800 people actually registered to that TIG. So it's a great resource. It's just not used enough, in my estimation. But certainly, one way or the other, we can help you out. So it's a great resource. Appreciate it.
Wonderful, thank you. And with that, we must conclude today's excellent online seminar. If you have any additional questions for our speakers, please send them via email to spe@compartners.com or the email address you see on your screen. Today's program is copyright 2012 by the Society of Petroleum Engineers with all rights reserved. On behalf of the Society of Petroleum Engineers, thank you to all of our speakers and, of course, all of today's participants. Have a nice day. You may now disconnect. On behalf of the Society of Petroleum Engineers, thank you to all of our speakers and, of course, all of today's participants. Have a nice day. You may now disconnect.